In this video, I want to explain the fixed point combinator. As one of my students said, fixed point combinator sounds like the name of some crazy sci-fi weapon. And indeed it is. So what the fixed point combinator will allow us to do is to start from a programming language and then add recursion to it. So we need syntax and semantics. So syntax, if you have a program E, we just create a new program for it, fix E. Semantics, the semantics of fix F is F of fix F. So from an operational point of view, you see that we unravel the recursion. We compute fix of F by computing F of fix of F. So this is unraveling the recursion once. From a more abstract point of view, this is saying that in our case, where we start from lambda calculus, what we are saying is that every lambda calculus expression has a fixed point. Lambda calculus expressions are functions, if you want. And we know what it means for a function to have a fixed point. But it's quite unusual to say that every function has a fixed point. So this is an interesting feature of lambda calculus. Okay, so what does that mean in a concrete example? Let's look at the factorial function. Factorial of n is if n equals 0, then 1, else n times factorial of n minus 1. So from the point of view of an interpreter, from the point of view of a machine, we don't know what factorial here means, right? So it's just a name. And so we can replace it by any other name. And so it's fair to rewrite this just to emphasize that factorial here is just any name. I just copied the right-hand side of the definition and replaced factorial by f. So f is just a generic function here. It's just a name for any lambda expression for any function for any program. And so what we're going to do next is to use our syntax from lambda calculus to say that what we have here is a function that depends on n. Right, so I put a lambda n in front because n is here our input. Now it's a function of lambda n, but really we can also think of it as a function of f. Yeah, because f is also just a name that we can abstract away from. And so the really cool idea here is that the factorial function, to compute the factorial function, it doesn't really depend on what f is at all. Yeah, so in fact, what we can say is that the factorial function is the fixed point of this expression. So the capital F that appears above in the semantics is this capital F here. And now let's see how this plays out if you want to compute something. So we want to at least test the case n equals 0, and then also the test where n is not 0. So the easiest example here, I guess, is factorial of 1. And remember now that the factorial function really is the fixed point of f, right? So that is the idea here. So in order to compute factorial function of 1, say, we compute fix f of 1. Okay, so how do we compute this? We need to use the operational semantics of the fixed point combinator. And if you remember from the top of the notes here, this was just f applied to fix f. And then 1 is our argument. Okay, so now here in this point, we see that f is a function. And it takes an argument. So we can do beta reduction and apply the variable f by its argument. So what does that mean? So it means that everywhere where we have the f, which is only here, we replace f by fix f. Okay, so let's do that. So this is beta reduction here, and it reduces to lambda n if n equals 0, then 1, else n times now fix f of n minus 1, and then we also have our argument. Okay, so here again we see we have a variable and an argument, so we can do beta reduction. So let's do another beta reduction, and we get if n equals 0. Okay, so what is the beta reduction actually doing? It's replacing n by its argument, so I should have written if 1 equals 0, then 1, else 1 times fix f of 1 minus 1. And now we reduce this. I think I make 2 steps in one go. Right, so we need now to use the computation rule for if then else. So this condition evaluates to false, which means that we choose the else branch. And then I'm also going, in the else branch, I'm going to use the computation rule for numbers here. 1 minus 1 is 0. So these are to do 2 steps in one go. And then this reduces to 1 times fix f of 0. Okay, so now you see that we are basically in the same situation as before. We started with a fix f1, and now we have a fix f0. And this is just what recursion is all about, right? Okay, so now we just keep on computing. The 1 times stays there, and we do the same step again. So maybe we can do it slightly faster now. So anyway, so the fix f turns into an f of fix f. And then the 0 is still here. Now, let me do the 2 beta reductions, which I have here and here, in one go. Right, so I replace the f by the fix f, and I replace the n by 0. So I get 1 times if 0 equals 0, then 1 else, what is our argument? 0 times f of, f is fix f, right? Fix f of 0 minus 1. And now we are in the situation where we have the true branch. The condition evaluates the true, so we go to the then branch. So this reduces according to the rules for if then else. This reduces to 1 times 1, and then our last reduction is just times tables. 1 times 1 is 1. Okay, so what you can do now is take pen and paper, compute factorial of 2, and see whether you can follow all the steps. Thanks for watching.